Hey everyone, and welcome to the Service Mesh with Istio course. I'm Sevi Karakose, and I'll be your instructor for this course.
Before we begin, don't forget to subscribe to our channel, as we post new videos every week.
Now to try Istio, let's deploy our application. In the samples folder we downloaded, you will find the sample bookinfo application. To deploy it, please use this command. If you have Istio samples somewhere else on your computer, you can also change this directory. In the output that follows, you will see a number of deployments and services created. Let's check the status of the pods deployed. We see that we have a pod for the product page microservice, the details microservice, the rating service, and 3 different versions of the review service. We see that everything is deployed in the default namespace. And now that we have Istio installed, we expected each pod to have the additional proxy container that we talked about. However, that is not to be seen. We can see that each pod only has a single container, as shown in the red column here. So why is that? We can use the istio analyze command to see why that may be the case. It seems that we have a problem here. The analysis tells us that Istio injection is not enabled. What does it mean by namespace is not enabled for Istio injection? You might be having multiple namespaces on your Kubernetes cluster. Kubesystem being the namespace where all the core applications run, and the default being the default namespace where applications are deployed when no namespace is specifically given, as it is in our case. There may be other applications running in other namespaces, such as HR or payroll, etc. You must explicitly enable Istio sidecar injection at a namespace level if you would like Istio to inject proxy services as sidecars to the applications deployed in a namespace. For this, as given in the output of the command, you must run the kubectl label command to specify the namespace where you want to enable sidecar injection by setting the value of the label Istio injection to enable. Similarly, if you'd like to explicitly disable Istio injection, then you must set this label to disabled using the same command. We will now delete what we deployed so we can set the label and deploy it again. Let's enable Istio sidecar injection in the default namespace. Once this command is run, every new app in the default namespace will get a sidecar automatically. Let's deploy our app again. Let's check the status of our mesh now. Let's check if we have Envoy sidecar proxies. Yes, they're here and running. Istio has now injected sidecar proxies into each pod. You will explore more about these in the upcoming labs. Well, that's it for now, and I'll see you in the demo. So, in this demo, we'll be installing Istio on our cluster using istio. For this, let's use istio install command. As we have talked earlier, for demo purposes, we'll use demo profile. Let's run this command now. Once installed, let's use the verify install command to check if everything is installed without any problems. As you can see, now in our cluster there are a bunch of new resources that Istio has added. Some of these are cluster roles, cluster role bindings, custom resource definitions, and 3 Istio deployments with 13 custom definitions. Our Istio cluster is installed and verified successfully. Let's move on to the next section. Let's have a look at gateways in Istio. Now that we have deployed the application and set up a service mesh, how can we make these services accessible to external users? In our case, the page that users need to view is the product page. How can we make the product page accessible to external users? Our requirement is that if someone goes to the URL http://bookinfo.app, they should view the product page with the details about all products. How can we achieve this? When we learned Kubernetes, we learned about ingress. Ingress controls traffic coming into the Kubernetes cluster. We learned that it is implemented by deploying an ingress controller such as an Nginx controller, and by defining a set of routing rules that route the traffic to the appropriate service. With ingress, we could configure rules to say any traffic to the Kubernetes cluster with the hostname set to the bookinfo.app should be directed to the product service. So here's a sample ingress object that we could create to drive traffic coming into the cluster at hostname bookinfo.app, so they are routed to the product page service. Now, this is Kubernetes ingress. While Istio supports Kubernetes ingress, there is also another approach that Istio offers and recommends that supports more Istio features such as advanced monitoring and routing rules. And that is called the Istio gateway. Gateways are load balancers that sit at the edge of the mesh. They are the main configurations that manage the inbound and the outbound traffic to service mesh. This is the recommended approach, such as compared to just using Kubernetes ingress. If you remember, we discussed earlier that when we deploy Istio on our cluster, it deploys 2 additional components known as the Istio Ingress Gateway and Istio Egress Gateway. These are Istio Gateway controllers, just like the ingress controller that we talked about earlier. The Ingress Gateway manages all inbound traffic to the services, and the Egress Gateway manages all outbound traffic from these services. We discussed that ingress is deployed in Kubernetes using controllers like Nginx. Istio, on the other hand, deploys ingress gateways using Envoy proxies. We have learned that all services have an Envoy proxy deployed as a sidecar container. However, the ingress and egress gateways are just standalone Envoy proxies, sitting at the edge of the service mesh. They do not work as a sidecar. These are the default gateway controllers that were deployed when Istio was deployed on the cluster. However, we can have our own set of customer gateway controllers as well. So our goal here is to catch all traffic coming through this Istio Ingress Gateway controller and route all traffic at hostname bookinfo.app to our product page. For this, we first create a gateway object. So here, we create a gateway object named bookinfoGateway. It serves all HTTP traffic at port 80 coming to the cluster through the Istio Ingress Gateway controller with the hostname bookinfo.app. But which Istio ingress controller? Here we have 3 controllers, the 2 custom ones we created. For this, add a selector and specify the label of the desired controller. In our case, we want to use the default Istio ingress gateway controller, so we set the selector ingress gateway. And we ignore the 2 custom ones we created. We then create the bookinfo gateway by applying this configuration. To list the created gateways, run the kubectl get gateway command. And to view details about a particular gateway, run the kubectl describe gateway command. So, we now have a bookinfo gateway object created to capture traffic coming through the default Istio ingress gateway controller through the URL bookinfo.app. But how and where is that traffic routed to? We will discuss that next when we talk about virtual services. So, let's try gateways in a demo. We already have a gateway configured. Let's check that one first. From the samples folder, we applied this gateway and it worked. As you can see, there's a wildcard in the host section. But how do we configure a gateway with a proper hostname? Before doing that, let's get the product page deployment created again from the bookinfo.yaml to make sure we have all our apps running. And here is our gateway. And I'm going to delete this one. Now, let us create a gateway with a specific hostname. Here is the YAML we can use for that. As you can see, it is using Istio ingress gateway and allowing traffic from port 80 on HTTP protocol, and it will allow in only the traffic coming to the bookinfo.app host. For this gateway to take effect, we need to create a virtual service to handle incoming traffic. And we'll have virtual services demo later on, but it is important to note that hosts need to match with the one in the gateway and the virtual service. So, this virtual service is bound to the bookinfo gateway we just created. In the virtual service configuration, there are some match rules and a route rule which we'll cover soon. For this gateway to allow traffic, we need to use bookinfo.app as our host in our request. In curl, we can add the -h flag to set HTTP header to bookinfo.app. Yay! It works! Now, our bookinfo application is open to outside traffic using our bookinfo gateway. Let's check it on Kiali's Istio config section. Here is the gateway, and you can also change some configuration from Kiali. And here's the virtual service we just configured. Let's go to our browser and try this hostname now. And in order to do so, we can add the IP and hostname to our host file with this command. Now let's try it. Here, in my browser, I'll type http bookinfo.app my port number / product page. And as you can see, we could go through the gateway we just configured using the bookinfo.app hostname. Now, I want to go back to the gateway and change the hostname back to wildcard. Because throughout this training, we might need to go back to default configuration using sample YAMLs to have a fresh start And as you might remember, we had wildcard in the hostname. So we'll stick to that format through this training and use IPs instead of hostname, if there's no specific use for that. Now, we can also revert the hostname in the virtual service back to the wildcard as well.
By the way, if you haven't done already, don't forget to subscribe to our channel.
Let us now learn about virtual services and Istio. So, we now have the bookinfo.app gateway. And users who are coming to http bookinfo.app will hit the gateway. But where to go from there? How do we route traffic through this gateway to our services? There are many different services. How can we specify that all traffic to the URL bookinfo.app/product page should go to the product page service? The product page service also serves static HTML/CSS and JavaScript contents at the path/static. There is also a login, logout, and API path. All of this should route to the product page. All routing rules are configured through virtual services. Virtual services define a set of routing rules for traffic coming from ingress gateway into the service mesh. Virtual services are flexible and powerful, with rich traffic routing options. You can specify traffic behavior for one or more hostname, manage traffic within different versions of a service, standard and regex paths are supported. When a virtual service is created, Istio control plane applies the new configuration to all the Envoy sidecar proxies. So let's create a virtual service to route these URLs to the product page service. We create an object with the API version set to the networking.istio.io/v1alpha3 as of this recording. Note that this may change in later versions, so always refer to the Istio documentation while creating virtual services to get the latest supported API version. Kind is set to virtual service. Metadata has name, set to bookinfo, and we have a spec section. First, we want to say that only traffic to the host bookinfo.app hits this virtual service, so we added a host section. There may be multiple gateways configured. How do we associate this virtual service to the gateway we created for our app? For that, we add a gateway section and specify the name of the gateway we created. That is bookinfo-gateway. And finally, we have the HTTP section where we add our routing rules. The match section specifies URIs that should be matched. These are the URIs that we just discussed. Exact means the URI is matched as is, and prefix are the URIs that start with the specified URI, such as /static/something or /API/v1/product/something. All of the traffic matching these URI patterns are then routed to the destination specified in the route section. So, we now have a virtual service for product page. All traffic coming in through the bookinfo-gateway with the hostname bookinfo.app now hits this virtual service. Next, the product page needs to talk to the review service. At first, it only talks to the version 1. And later, we bring in versions 2 and 3. How do we gradually introduce the other versions and only drive a small percentage of traffic to it and test them before driving all to it? Let's first look at how this works without Istio or virtual services on a plain Kubernetes cluster. So, in the beginning, we have the product page service talking to the reviews v1 service. We then came up with two new versions of the reviews service, version 2 and version 3. Version 2 has the black stars, and version 3 has the red stars. We want to test these services by driving a small percentage of traffic to it until we are sure they work as expected and that our users like the new star feature. In the plain Kubernetes world, without Istio or a service mesh, we would deploy the reviews microservice as a deployment. Let's say it has 3 replicas, for example. This microservice is exposed within the cluster using a service type of cluster IP. The label's app is set to the value of reviews, and that helps the service identify the pods as part of the reviews deployment. The service directs traffic to all the 3 pods. The product page can now refer to the review service to get reviews of a book. As of now, 100% of traffic goes to the reviews version 1. When we deploy a new version of the review service, say version 2, we create it as a new deployment. But to begin with, we only deploy one pod, because we don't want all users to go to that service. We use the same label though, a label called app with its value set to reviews. And as such, the same service picks up the new pod, part of the new deployment. Now, the service has 4 endpoints. As such, 75% of traffic now goes to version 1 and 25% goes to v2. Now with the third version of reviews, we deploy a new reviews application. This too has a single replica and the same labels. So the service now has the new pod added as an endpoint. And now with the new pod, 60% of traffic is routed to version 1, 20% to version 2, and 20% to version 3. So, let's say for instance, we have identified version 3, the one with the colored star, to be the winner as users like that the most. So, we decide to route all traffic to that version. For this, we first scale up the replicas of version 3 to 3. So now we have an equal amount of traffic going to version 1 and version 3. We then scale down the replicas on version 1 and 2, and now we have 100% of traffic to version 3. We now have successfully run an A/B test to route traffic to the new versions, tested and identified the correct version to use, and then migrated to the new version of review service, all live and without any downtime or disruption to service. This whole process is the native Kubernetes way of performing canary tests and controlling traffic between different versions of services. However, this has several challenges. Earlier, we had 100% of traffic going to version 1. And then version 2 was deployed. We had 75% going to version 1 and 25% going to version 2. What if we need more granularity in distributing traffic between versions? For example, what if we wanted to send just 1% of traffic to version 2? So that the distribution is 99% to version 1 and just 1% to version 2. Since there are only 4 pods, and since the Kubernetes service distributes traffic across all of them equally, the distribution can only be 75 and 25%, not anything else. The only way to change the distribution percentage is to play around with the number of pods available in different services. So that's a limitation. With Istio and virtual services, we can now create a virtual service instead of a service, and we will call it reviews. We then define two destination routes for traffic distribution, subset v1 and v2. And we set a weight for each. 99% for one and 1% for the other. Now, we can route 99% of traffic to one service and 1% to the other. Even if the reviews v2 service had 3 or more pods, the traffic distribution would still be 99% to v1 and 1% to v2. The number of instances now has nothing to do with the traffic distribution, and we can easily control that through the virtual service configuration. Now, you must be wondering what a subset is and how it is configured. Well, hold on to that thought. For now, just think of it as a way of grouping multiple objects together using a label, like how a regular Kubernetes service is. But not exactly. We will get to that in the upcoming sections. For this demo, first we'll change the weight of our reviews application between its different versions. Then, we'll create some routing rules so that different users will see different versions of our application. To be able to change the weight of traffic between different versions of an app, first we need to define those versions. This can be done by using destination rules, as we've talked earlier. For this demo, we can use the default destination rules from our samples folder. Then, let's create our virtual service. This virtual service will be named reviews, and it will be affecting reviews host. Under the HTTP route section, we have created two different destinations. First is for subset v1, that is defined by a destination rule. Second is for subset v2, and that is also defined by a destination rule. And you can see there's a weight distribution by 75 to 25 here. These numbers always need to be 100 when summed up. We can apply this YAML now. Let's check with Analyze if it's all good. Yes, it's all looking good. Now, let's create some traffic to our application to see how this change in weight will affect it. Switching back to Kelly for that, we can check the Istio configs. Here are the destination rules we created from the samples folder. As you can see, there are 3 different subsets that will be matched by the services labels, version v1, v2, and v3. Let's check out Reviews virtual service. You can see the weight distribution in this bar on the right. Now, let's see the graph. As you can see, the weight of all review service is distributed between v1 and v2. When we go to the app, it shows that there is only a no star and a black star version. Red star version is v3 and it is not there. Now, let's stop the loop that we have the traffic coming from and try to feel the 75-25% difference in the browser. As you can see, version 1 is more common than version 2. I've just stopped the other traffic source, so the balance might not be very clear right now, but you can see the difference. Now, let's change our weight distribution once more, but this time we'll do this using the Kelly interface. This time, I'm adding another destination, but I'm not changing any weight, so it will be 125 in total. Let's see how it will go. As you can see, Kelly interface did not let me save this, and it has given me a proper error on the X at the top. Let's fix this weight distribution. And also I want another subset v3 here. So as you can see, first we had only 2 versions of reviews, and we now, even for a small percentage of requests, introduced another version of it. We can check it in the browser, and it is not common, but we've started to see some red stars in some of the requests. Let's go back to the terminal and create some heavy traffic here. As you can see, v3 is also in our graph now. There are different graph versions here. Some show them grouped as services, some show them grouped as workloads. Let's check Istio virtual service config. Here on the right, you can see the new weight distribution. If you click hosts, you can also see the overview of the hosts. Well, in this detailed graph, it will give us some more information about weight distribution. As you can see, Reviews version 1 traffic is almost 3 times more than version 2 and version 3 as we've configured it. Now, let's try the example we used in the lecture. Let's try to distribute traffic by 99% to 1%. Yes, version 1 and version 2, okay. We can remove version 3. This probably will take some time. Okay, we've waited a bit, and as you can see, the weight of Reviews version 1 traffic has changed drastically. And it will probably change some more over time. And also in the browser, we cannot see the second version, almost at all. Ah, there it is. Now, let's do another example. Let's remove the other destination. We want some of our users to see some specific versions of our app. For example, our product owner might have said, everyone has a non-star version, but for a special user group called KodeKloud, they want to release a starred version of our app, which is a very nice and rich feature. And let's add a new section under HTTP for that, called Match. When KodeKloud user signs in, they'll see the black star version, and the rest of the users will see the regular one. To do that, we'll now add a rule. This rule will pick the requests that have end user in the request header, and it will check if it's matching exactly with KodeKloud. If a request passes this rule, it will be routed to Reviews version 2, and the rest will be routed to Reviews version 1. But how do we create a request that has KodeKloud end user in the request header? Don't worry about it. We have a feature in our application. See the tiny sign button on the top? That's for adding an end user header to the request. We'll just type our username and write a random password, then sign in. There's actually nothing this app does in terms of checking this user. It is just for experimenting with request header. Once you sign in, you'll see the Reviews version has changed to version 2. And it is not related to a weight distribution rule at all. I keep refreshing, but the page is still the same. However, when I sign out, it changes back to version 1, just as we configured it to do. Now, we are happy with this, but we also want to introduce a new version for a specific group of people, and we want them to test it, and they can even give us some feedback. For this, let's create another match section. and give a very secret name to these users as test users, okay, and route that traffic to our newest very colorful version 3. As you can see, the bar on the right shows both 3 routes are 100% in weight once they've matched our rules. Now, let's try the default version without signing in. Yes, it's a no-star version 1. Let's try if our new version is available to test user. It is working and there is nothing else test user can see. And KodeKloud user is still seeing the black star version with no problem at all. Virtual services are powerful, and as we've just experienced, they can help you manage your traffic with much flexibility. Let us now have a look at destination rules. Destination rule applies routing policies after the traffic is routed to a specific service. Let's see what this actually means. Earlier, we talked about virtual services and how the review service can be configured with a virtual service to distribute a percentage of traffic to different versions. We know that 99% of traffic is sent to the subset V1 and 1% is sent to subset V2. So, where and how are these subsets defined? Subsets are defined in destination rules. So, we create a destination rule with the kind set to destination rule, name set to reviews-destination, and host set to reviews. We then define 2 subsets, version 1 and version 2, and provide labels under it. We set the version to version 1 and version 2 respectively. These are the labels set on the pods for the respective version of reviews deployment. This is how we define separate subset of services so that we can control the amount of traffic going to each subset. By default, Envoy load balances traffic in a round-robin fashion. This can be customized through the destination rule by specifying a traffic policy of load balancer. Set the traffic policy to a simple pass-through policy. This will route traffic to the host that has fewer active requests. There are other simple algorithms such as round-robin, random, and pass-through. What if we want to override a different load balancer policy for specific subsets? For example, for subset V2, we would like to have a random load balancer policy. For this, we can specify a traffic policy at the subset level like this and configure a different policy. This way, we can configure one load balancing policy for all subsets and a separate one for selected subsets as required. There are many more configurations supported by destination rules. For example, to configure a client to use TLS, specify simple TLS. Or to configure mutual TLS, set the mode to mutual and provide the path to the certificate files. One important thing to note is the host field here. It is currently set to reviews, which is the name of the service. It is the short name of the service. When using short names instead of fully qualified domain names, Istio will interpret the short name based on the rules namespace and not the service's actual namespace. This might lead to misconfigurations if your service is another namespace. To avoid this, using fully qualified names over short names is recommended. Well, that's all for now. In this video, we will talk about fault injection. So, here is what we have done so far. We have deployed the application, configured a gateway, set up the product page virtual service, and the reviews virtual service. And it's all working as expected. Next, we would like to introduce some errors to check if error handling mechanisms are working as expected. And that is fault injection. This is a testing approach, and it helps us to see if our policies run efficiently and are not too restrictive. We can inject errors in our virtual services, and these could be two different types of errors: delays and aborts. In this example, we are injecting a delay type of faults in the mesh for ratings virtual service. Since it's described as percentage, it will add a delay for 10% of requests, and this delay is configured as 5 seconds. Apart from delay, you can also configure abort to simulate errors by rejecting requests and returning specific error codes. Let us now talk about timeouts. When it comes to software, we must know that anything could happen. Since each service within this microservice architecture is a software, we should expect them to slow down, fail, or go completely crazy for no obvious reasons. And since the services are dependent on each other, slowness on one service might affect the other services dependent on it, and even have a cascading effect. For example, if the rating service slows down for some reason, we will have requests queued at it, which is going to cause requests on the review service to be queued up, which is going to cause the requests on the product page to be queued up. So, let's say, for example, the details service slows down. Then the requests coming from product page to details service is going to get queued up, and the request to product page itself is going to get queued up, affecting all users accessing the application. That's why we need timeouts. If a service is taking too much time to respond, it must not keep the dependent service waiting forever. It must fail after a period of time and return an error message. That way, the dependent service gets an error message and is not impacted. That's what a timeout is. We can either configure a timeout at the details service for it to fail, or we can configure a timeout at the product page service for it to fail sooner rather than waiting for the details service for eternity. So, here we have the details service and the bookinfo service that directs traffic to the product page. We want to add a timeout to the product page service to reject requests if it takes more than 3 seconds. For this, we add a timeout option and set it to 3 seconds. Now, since our app is working perfectly, how do we test this? Because we don't have that much traffic and our details service works perfectly. We want it to fail. That's what we learned in the previous lecture. We could simulate a failure using fault injection. For this, we add a fault section to the details service with a fixed delay of 5 seconds and we inject this failure for 50% of the traffic. Well, that's it for now, and let's see this in action. Let's talk about retries. When a service tries to reach another service, and for some reason it fails, we can configure the virtual service to attempt that operation again. This way, you don't have to handle retries within the application code. You can configure retry settings, which basically says the number of times to try and the interval between them. Istio by default has a retry behavior which is 25 milliseconds between retries and retrying 2 times before an error returns. Let's examine a retry setting. Like timeouts, retries are also specified on virtual service level. You can set the attempts to try before it gives up and returns an error. And you can set the delay between each try as well using the per try timeout option. So, we are at the end of this course. I would like to thank you for watching this course. I hope you enjoyed all the videos and labs. If you like the course, please don't forget to share it with your friends on social media. Until next time, this is Sevi Karakese signing off. Goodbye.
By the way, if you haven't done already, don't forget to subscribe to our channel.